The ratio between transverse strain and axial strain when force is being applied along an axis is called the Poisson's ratio. Most materials have positive Poisson's ratios, meaning they expand in the direction parallel to the applied force and contract in the direction perpendicular to the applied force. If a material exhibits a negative Poisson's ratio, they will expand in both the axial and lateral directions when a force is applied in tension. However, they will contract in both directions when a force is applied in compression. A normal material will get thinner when stretched, while a negative Poisson's ratio material will get thicker when stretched. Notable materials with negative Poisson's ratio include graphene, polyurethane foam, tendons, and folded paper. Shear modulus is a relationship between elastic modulus and Poisson's ratio. The higher the value of shear modulus, the more rigid the material. Rigid materials display less elastic deformations under load and are more prone to brittle failure. This results in the ability to absorb high amounts of energy while deforming plastically without fracture. Negative Poisson's ratio materials, also known as auxetic materials, show higher shear modulus, which enhances their hardness and toughness. Commonly found auxetic structures include microporous polytetrafluoroethylene, trial honeycomb, bowtie, and 3D auxetic lattices. Auxetic materials can be created by laser sintering, where a 3D CAD model is used as a blueprint. A computer analyzes the blueprint of the model and guides a laser to create a layer of structure by fusing metallic powder together. After each layer, more powder is placed on top to create the next layer until the structure is complete. Laser sintering provides the structure with a high degree of accuracy. Another way to create auxetic materials is to use photolithography. Photolithography takes advantage of the difference in solubility when light is exposed to a photomask. By etching a design on the photomask, chemicals can be used to dissolve a region of the structure while keeping other parts of the structure intact. This can be used to make repeating structures on a microscopic scale. Auxetic materials show enhanced mechanical properties such as increased shear stiffness, increased plane strain fracture toughness, and increased indentation resistance, all of which make them superior to classical materials for many practical applications. Lightweight auxetic composites can be used to enhance the ballistic and impact-resistant capabilities of armored vehicles. Auxetic materials can also be used to make textiles. Auxetic textiles can be used for clothing and safety equipment, such as helmets, safety vests, and shoes. Some shoe companies have already started to sell shoes with auxetic technology for better fit and support. Additionally, auxetic structures are currently being applied to fibers. For example, the biomedical field is researching auxetic fibers to be used as bandages. These bandages can deliver medication more efficiently and safely to the patients. As the fibers are being stretched, the micropores of the fibers would open and release the correct dosage directly at the target area. Finally, auxetic materials can be used for blood vessel stents. A stent is a small mesh tube that is used to increase blood flow to narrow or weak arteries. A traditional stent may not always open up all the way to bolster the flow in the blood vessel. On the other hand, a stent made from auxetic materials can expand to volumes much larger than a regular stent. That's all. Thanks for listening.